All right, so welcome to Math 150, Lecture 24. While we're waiting for people to come in, I'm just sharing some thoughts about statistics as we wait for the dominoes challenge. People do the dominoes challenge. So the dominoes challenge, if you want, is take a bunch of dominoes and see what is the maximum overhang you can have to either the left or the right just using the dominoes. So here is a wonderful web shot from June 4th, 2018. Depending on which website you go to, either the Red Sox or the Yankees are in first place. They both sides list the same record for the Yankees, both sides list the same record for the Red Sox. How can they have a different opinion as to who's in first? No. And in fact, if you look on the right, it lists the Yankees as in first, one game back of the Red Sox. So one side is based on win percentage. So the one on the right, the Yankees have 6 more wins. I'm sorry, the Yankees win percentage is a little bit higher than the Red Sox. The Red Sox have played 6 more games. The Red Sox won 4 wins, 2 losses in 6 games. Now, normally, if you win 4 out of 6 games, that helps your winning percentage deep in the season. But this was early enough in the season that the Sox and the Yankees were both playing so abnormally well that the Red Sox winning 4 and losing 2 actually lowered their winning percentage. And so the Yankees are slightly ahead in terms of winning percentage. You basically get half a game for each win, you lose half a game for each loss. So the Red Sox are technically 1 game ahead of the Yankees, even though by winning percentage, the Yankees have a slightly higher winning percentage. This is also an example of it doesn't really matter because by the end of the year, the teams will have played the same number of games. I was giving a talk on this recently, and I went back to 2018 to the websites to try to just get a better snapshot than what I had outside my office. How many people have ever read 1984? If you haven't read it, you should still read it while you can. So they have the Ministry of Truth, which goes back and it changes previous records to match what the current views are. And if you go back in time on the web and look at June 4th, 2018, it no longer has these statistics. What had happened is one of the reasons the Sox had played 6 more games than the Yankees is one of the Yankee games had a rain delay. And when the game was finished months later, it is credited as when the game started. And so then they retroactively went back and changed the statistics. Because of this, you have some very interesting bookkeeping in baseball. Somebody actually has their first major league home run 5 days before they were called up to the majors. Because there was a game that was postponed, he was then called up maybe a week or so later, and when the game was postponed, he hit a home run in the postponed game, and it then technically counts as now his first game. So you've got to be very careful when you look at things, trying to find what is the right statistic. So the domino challenge was, what's the largest overhead you can build using dominoes? Well, the method, or to decide how much of a credit I should give you, it should be a function of how many dominoes you use. If you can get an overhang of 1 domino using 1,000 dominoes, that's not nearly as impressive as an overhang of 1 domino using just 20. And so I'll talk a little bit later today about different ways of looking at this problem. That's what I want to do now. I want to shift to the main slides. Okay. So for today, what I want to do is just review what sequences and series are. I'll talk a little bit about necessary versus sufficient conditions for the convergence of a series. We will talk a little bit about P-series, especially harmonic and applications to primes. I am going to give one of the most painful proofs I think you will see this semester to show that one of these series converge, to just really motivate why we're going to learn the integral test. The integral test is much easier. You often do not truly appreciate something until you see what it allows you to get out of doing. Talk a little bit about the comparison test. I want to make sure we get to at least some applications of what we're doing there. Who gives a damn? Why are we spending our time doing this? So we've talked a little bit about, we care about convergence because we want to talk about Taylor series. We want to approximate complicated functions with simpler ones. So I'm going to give an example of this by discussing how streaming video works. I know everybody has at least streamed something because you're watching the classes beforehand. And I'll talk a little bit about how you can hide messages in messages. So there will be a cat hidden in one of the slides today. the cat will be of size at least 1/8 of the image. And you can see the cat before I pointed out it is worth $100. Okay, so the first thing we're going to do is sequences and series. So a sequence is a collection of terms. A series is the sum. So maybe I have, the sequence AN. I really wish I knew how I just switched the colors so quickly. AN might just be 1 over n. Or maybe it's 1 over n squared. Or maybe it's 1/2 to the n. Those would all be different sequences. And so for this one, the terms would be 1, 1/2, 1/3, ... This would be 1, 1/4, 1/9, ... This would be 1, 1/2, 1/4, ... And the first question is, what is the sum? So sum n goes from 0 to say big N of AN, and does the limit exist as n goes to infinity? So for one of these sequences, we know it has a finite sum as n goes to infinity. Does anybody know which of these series has a finite sum as n goes to infinity? So you have 1, 1/2, 1/3, 1, 1/4, 1/9, 1, 1/2, 1/3. One of them we've already done, yes. I believe it's, yes, and this is the geometric series. So this converges. This converges as well. This is the harmonic, and it diverges. So I'm going to first do a necessary condition for a sum to converge. We need AN to go to 0 as n goes to infinity for the sum n goes from 0 to infinity of AN to converge. If the individual terms aren't going to 0, there's no way the sum can converge. What does it mean if the terms don't go to 0? Well, one possibility is they're always at least a certain amount in absolute value. What does it mean if it doesn't converge to 0? It means no matter how small of a window I take around 0, infinitely often I'm outside of it. So infinitely often I'm getting a boost of at least maybe plus 1 over a billion or minus 1 over a billion. So I'm having a significant movement infinitely often. Does everyone agree that I need my terms to go to 0 for the series for the sum to converge? And this is a necessary condition. It's not a sufficient condition. And there's a whole slew of examples you can use. This is probably my favorite. Anybody want to tell me what comes next? 1, 1/2, 1/2, 1/3, 1/3, 1/3, 1/4, 1/4, 1/4, 1/4. Yep. And I'm clearly choosing this so that each of these sum to 1. And so the terms tend to 0, but the sum diverges. So this is the simplest example I know where you can see the terms are going to 0, but the sum doesn't converge. All right, so the harmonic series diverges. And we'll see 2 proofs of it because it's so important. It's 1 plus 1/2 plus 1/3 plus 1/4, 1/5, 1/6, 7th, an 8th to a 15th, and so on. Everybody agree that 1/2 is at least 1/2? What about 1/3 plus 1/4? How large is that? That's at least 1/2. Why is it at least 1/2? Yes. Yeah, it's at least 2 times 1/4, which is 1/2. And for the next one, this is at least 1/2. It's at least 4 times 1/8, which is 1/2. So what we show is that if we keep moving in blocks of size of powers of 2, we're going to get at least 1/2. So this gives us a lower bound that if we sum n terms, so the sum n goes from 1 to n of 1 over n is greater than or equal to something like the log base 2 n times 1/2, something like that. With a little bit of work, if you do things in the other direction, you can get an upper bound. Yeah. 1/3 is going to be greater than 1/2. 1/4 plus 1/5 plus 1/6 plus 1/7 is going to be, I'm sorry, 1/3 is going to be greater than 1/2. No, 1/2 is going to be greater than 1/3. 1/2 is going to be greater than 1/4 plus 1/5 plus 1/6 plus 1/7. And so you can get an upper bound as well. So similarly, it's going to be less than or equal to something like the log base 2 of n times 1/2. So this argument tells us not only does the harmonic series diverge, but it looks like it's diverging like the log of the number of terms. So we have some idea of how quickly it's growing. All right, I want to do another proof that it diverges. So assume the harmonic sum converges. So I'm going to write S as 1 over 1 plus 1/3 plus 1/5 plus 1/2 plus 1/4 plus 1/6. So it's going to write S odd plus S even. I'm going to break it into the odds and the evens. Which do you think is large? The sum of the odds, the sum of the evens, or do you think they're the same? Okay, why should the odds? They're both finite sums. So why would the odds be larger?
Like each term is, like if you compare the first term with the first term of the even.
Yeah, 1 over 1 is greater than 1 over 2. 1 over 3 is greater than 1 over 4. And so on. But this nice relationship between the sum of the evens and the entire sum. Does anybody know the relationship between the entire sum S and the sum of the evens? One half plus 1/4 plus 1/6. Against 1S minus S. So S minus S1 is S even. But there's a nice relationship directly between S and S even without using S odd. You get 1/2, 1/4, 6, 1/8. What do you notice about all those fractions? What do they have in common? And could do n plus 2, but it's better than n plus 2. It's each, I can pull out a 1/2. So it's 1/2, 1 over 1 plus 1 over 2 plus 1 over 3. Oh, that's just 1/2 times the entire sum. Right? This is a really powerful observation that if you have something that's just evens, I can pull out a factor of 2 and I just have to everything again. So I have S is S odd plus S even, which is strictly greater than S even plus S even, because S odd is greater than S even. But this is just twice S even. And what does twice S even equal? That's just our sum S. So assuming S is finite, yields S is strictly less than S. Oh, sorry, strictly greater than S. Well, of course, I could just move things around. Contradiction. So this is a really powerful way of proving results. This is a proof by contradiction. We assume what we're trying to show is false. We assume something, and then we get to a contradiction, and then that means our assumption must be wrong. So hopefully there's only two possibilities. And for this, there's only two possibilities. The sum converges, the sum does not converge. Let's assume the sum converges. We get a contradiction. Okay. The only thing we assumed was the sum converges. That assumption must be false because it led to a contradiction. Technically, you could also say, well, that doesn't prove that the sum converges. It just proves either the sum converges or all of mathematics. Well, we're assuming that the sum converges. So if we assume the sum converges, then I can break it up into the sum of the evens and the sum of the odds. You've got to be careful. As everything has a positive sign, you can still do something like this. But you always want to be careful whenever you have infinities. Because everything converges, I don't have to worry. If you rearrange terms that have negative signs in them and positive signs, weird stuff can happen. Because everything is positive, and I'm assuming things converge, let me group all the odds together, let me group all the evens together. Because everything is non-negative and it converges, the sum of the odds converges to something. The sum of the evens converges to something. So let's call that S odd and S even. And then we get, well, S odd is clearly larger than S even. But S even is 1/2 the total sum. And this leads to a wonderful contradiction. Any other questions on the harmonic series? So one of the reasons I was giving you the dominoes, I'll try to. So in trying to do, what is the largest overhang we can do with a bunch of dominoes? It turns out that if you do the standard approach of just putting each domino and then having the next one a little bit further to the right and the next one a little bit further to the right, what you want to do is you want to move things harmonically. So the first one is moving over at the halfway point. The next one is then moving over a third, and so on and so on. Or maybe it's sort of here, a halfway point, and then maybe it's this way, maybe it's that way. Yeah, I think it's that way. I think I had it. So you start off with a half, and then you put the one underneath it, and you move it like that. And that keeps the center of mass where you want. So if you discovered that, that's good standard thinking. If it wasn't COVID, I would ask somebody to come up here and help me. But in the COVID era, I don't think I'm allowed to do that anymore. If you can think outside the box a little bit, what you can do is something like this, where I now have an overhang going left and right. And if I start building structures like that, you can go remarkably far. And so this is a wonderful example of sometimes it's better to take one step backwards to take 2 steps forward. And so if you go with a harmonic approach, the maximum distance you can get with n dominoes is basically the sum of the harmonic series, which if you sum the first n terms is about 1/n. If you do these things working, going backwards, you can actually get things, it's either n to the 1/2 or n to the 1/3. My math professor from my first year in college is one of the people on the paper that analyzed and proved how far you can go. And what I love about this problem is it just shows you how it's so easy to have blinders on that when you're doing a problem, you put in additional assumptions that aren't there. The assumption is, well, I should keep moving to the right. Not necessarily. Sometimes it's worthwhile to take steps to the left and right simultaneously. And so at every moment in time, I may not be moving the best I can, but overall, at the end of the day, I am. And so if I have time later in the semester, we'll go back and talk about like the drowning swimmer. Right, the next one I want to do, and this is going to be one of the worst proofs in class, is I want to prove the sum of 1/n squared converges. So I have 1 plus 1/2 squared plus 1/3 squared plus 4 squared, 1 over 5 squared, 1 over 6 squared, 1 over 7 squared, 1 over 8 squared, 1 over 9 squared, and so on. And what I'm going to do is I'm going to break it up into blocks, where each block is twice as large as the previous. So in block K, I go from n equals 2 to the k to n equals 2 to the k plus 1. So 1 over n squared goes from 1 over 2 to the k squared to 1 over 2 to the k plus 1 squared. Does everybody see that that's just 1/4 1 over 2 to the k squared? So in this range, 1 over n squared is less than or equal to 1 over 2 to the 2k, and it's greater than or equal to 1/4 1 over 2 to the 2k. The whole point of this is called localizing. I'm trying to understand what's going on. My function 1 over n squared is varying a little bit, so I can zoom in and I can take a bunch of n's that are of similar size. And I can get an upper bound. Everything in this range is at most 1 over 2 to the 2k. And I can get a lower bound. Everything in this range is at most 1/4 1 over 2 to the 2k. And so now if I want to try to understand what's going on, I can get very good upper bounds and lower bounds. This is that should be -1. So I go to 1 less. And so the number of terms is basically 2 to the k. So the first one, when k equals 0, I have 1 term. When k equals 1, I have 2 terms. When k equals 2, I have 4 terms. So I have 2 to the k terms, and each term is basically of size 1 over 2 to the 2k. So if I want to study the sum of 1 over n squared and goes from 1 to infinity, this is going to be less than or equal to the sum. K goes from 0 to infinity. I have 2 to the k terms, and each term is v at most 1 over 2 to the 2k. And similarly, it's going to be greater than or equal to the sum. K goes from 0 to infinity of 2 to the k over 4 times 2 to the 2k. Let's look at this. What is 2 to the k divided by 2 to the 2k? So 2 to the k divided by 2 to the 2k, what is that? So we're going to use our algebra. 2 to the negative k. So this is 1 over 2 to the k. What's the sum? K goes from 0 to infinity of 1/2 to the k. 1/2 to the k. What kind of series is this? Geometric. Which geometric series is it? Just 1/2. Geometric with the ratio equals 1/2. So we have a geometric series where the ratio is 1/2. Does that sum converge or diverge? Converge. And in fact, we know what it converges to. It converges to 1 over 1 minus 1/2, or 2 what? 2. Right? So we get 1/4 of 2 is less than the sum and goes from 1 to infinity of 1 over n squared is less than or equal to 2, or 1/2 less than or equal to the sum and goes from 1 to infinity 1 over n squared is less than or equal to 2. One of these bounds is good, one of these bounds sucks. What do you think is the good bound? 1/2 or 2? One of the bounds should not impress you. unless you're really easily impressed. If you have substandards, one of these bounds should not be that. Yes, no, it doesn't start at 1/2. What does it start at? The first term is 1. So 1 plus 1/4 plus 1/9 plus 1/16, it's at least 1/2. How? Yeah. Thank you. There's easier ways to prove that the sum is at least 1/2. The simplest being, well, the first term is 1 and everything is non-negative. So the 1/2 isn't that impressive. The fact that it's at most 2, that's actually impressive. It turns out this is the basal problem. Euler was the one who solved it. It's pi squared over 6. And because pi is irrational, this actually implies that there are infinite many primes. So there's a lot of really wonderful math working in the background on this problem. But does everyone agree that this is a little bit of work to prove that this converges? We had to break things up into groups of powers of 2. We had upward and lower bounds for each region. There's a lot of great ideas lurking. But when we get to the integral test, I think that's going to be the next lecture, we're going to see a much faster way of studying and solving problems like this. All right. So we've done sequences and series of definition. We've talked about a necessary versus sufficient condition. We've started to talk about P series. We did the harmonic series. We did 1 over N squared. And so the question is, could we do things a little bit more general? Well, I did here 1 over squares. If instead of squaring things, if I cubed things, would that make it diverge? Replaced 1 over 2 squared with 1 over 2 cubed, 1 over 3 squared with 1 over 3 cubed. If it converged when I did the sum of these, yes. Yeah, so everything's going to be small. So if I have a sequence of non-negative numbers and it converges, then another sequence that's smaller than it 2 by 2 would converge. So I immediately get that it would converge if I used cubes or quadrants. If instead of using squares, what if I did the 3/2 power? Now I wouldn't know because now I'm making the denominators smaller, so the sum becomes larger. But if you look at this argument, the key thing we had was 2 to the k over 2 to the 2k. If instead we had the sum 1 over n to the p, n goes from 1 to infinity, this is less equal to the sum k goes from 1 to infinity of 2 to the k. And then we had 2 to the k, but now we'll have it to the pth power. And this is going to be the sum k goes from 1 to infinity, and we'll have 1 over 2 to the p minus 1 to the k. So if p is greater than 1, it converges. If p is less equal to 1, it diverges. And we call this a p series. Anybody know why we call it a p series? What the p stands for? Think of a word that starts with P that might describe this. Not part of too many things possible. How? I'm not sure. If I had to guess, I would guess it's because it's a how. Okay? All right, so we've just shown that the sum of 1 over n to the p converges whenever p is greater than 1. It diverges whenever p is less than or equal to 1. The argument we gave actually works in great generality. It's a tough argument, but it works. We're going to see a much better argument probably next class when we get to the integral test. So we've talked a little bit about the comparison test. So let me write it down explicitly. Assume 0 less equal to an less equal to bn, or 0 less equal to Cn less equal to An. If the sum of Bn converges, then the sum of An converges. If the sum of Cn diverges, then the sum of An diverges. So if you have a non-negative sequence and term by term by term, it's less than something that converges, then its sum converges. If you have a non-negative series and term by term by term, it's greater than a non-negative series that diverges, then it diverges. So the comparison test is a great way to determine if something converges or diverges. The problem with the comparison test is you have to figure out what to compare it to. So I always like to view this as in calculus, not calculus, in algebra. If I give you x squared minus 7x plus 12 equals 0. Anybody tell me the roots? Yes. Nope. 1. So I know because I have a negative sign, I have to have at least one negative term. Because I have a plus 12, I know I have to have both negatives. And so now, how can I write 12? I can write 12 as 1 times 12, 2 times 6, 3 times 4. It's got to be 3 times 4. What if instead I give you x squared minus 7x plus 11 equals 0? How would you find the solution? Calculator over, there's an electromagnetic pulse, all calculators have been disabled. Quadratic form. So it'd just be 7 plus or minus the square root of 49 minus 4 times 11 all over 2. So we have a mechanical procedure we can go through. And we may not enjoy doing it, but we have. There is one for cubics, there is one for quadrics, there is not one for quintics and higher. Which is faster? I mean, I could have used the quadratic formula, x squared minus 7x plus 12 equals 0. Okay. I could have said that the solution is going to be 7 plus or minus the square root of 49 minus 48 all over 2. And you'll see, oh wow, 49 minus 48, that has a really nice square root, everything's going to be fine. Why didn't I use the quadratic formula? Yeah, if you are comfortable enough to just quickly look at it, it's often faster to just quickly look at it and see the solution rather than going through the quadratic formula. This is how you should view all of these tests. If you can just see a fast way to use something, do it. The problem is you have to be creative. You have to find the right way to look at it. So if you want to use the comparison test, you can't use the comparison test if you don't know what to compare it to. That's where this becomes a bit of an art. We will learn the ratio test, the root test, the integral test. For the most part, these are extremely straightforward in terms of just do some algebra, just do some integration, and you'll get the answer if you can do the algebra. You don't have to think what to do. What's lurking in the background of all of these is the comparison test. It's just the comparison test is being done for you automatically. And the ratio root test, they know what series to compare to. They compare to a very special geometric series. Whenever you see a theorem, you always want to talk about the conditions. So I'm assuming that I have a sequence of non-negative terms. So imagine an is less equal to bn, and the sum of bn converges. Can the sum of an diverge? So no longer assuming an is non-negative. Can you give me a series Bn that converges and a series An that's less than a term by term, but the sum of An will diverge? So we want to give me a series Bn that converges. So give me a series that converges. One over n squared. We just showed it converged. Let's call it up to the big leagues. It's going to be clean. Give me a series An that diverges, and An is less equal to 1 over n squared for each n. So what can I take for An? Could I take 1 over n? I know 1 over n diverges. No, because 1 over n is actually larger than 1 over n squared. If you try to use the comparison test and you took, Cn is a series that converges, and then you have An, which is larger term by term, you would know that the sum of An is at most, I'm sorry, is at least a finite number. All right, really useful, thank you. Yeah, I want to know, is it a finite number? It's at least finite. Okay. Can somebody give me a good choice of a that's less 2 by 2?
Whatever n cubed.
Okay, but 1 over n cubed is going to converge. I want some of a to diverge. So I removed a condition. What condition have I removed? The non-negative. But 1 over negative n cubed is still going to converge. But n goes from 1, 2, 3, 4, right? You're making this too hard. Yes. Okay, but that's going to be larger than 1 over n squared. So it's going to be something negative. Give me a negative number. Negative 5. So let's have our sequence the following. What should the next number of our sequence be? Nope. Nope. Simplest thing possible. You gave me negative 5. What are you going to give me again? Negative 5. What are you going to give me again? Negative 5. Just keep taking the same thing. Negative 5 is less equal to 1 over n squared. Because I've dropped the condition that it has to be non-negative, I can just take the same number again and again and again. And this shows you that you really do need the condition that it has to be non-negative. So the next one is, imagine we have, Cn less than equal to An, and the sum of Cn diverges. Does the sum of An have to diverge? So can somebody, it's going to be something involving negatives. Somebody give me a sum of Cn that diverges. So I could do Cn equals negative 5. Try Cn equals negative 5 for all n. And take An to be what? Take our 1 over n squared. So these conditions really are necessary. So one of my professors, Peter Jones at Yale, said, if you remove a condition from a theorem, usually the theorem is much harder to prove or false. And so if you remove a condition, you should often be able to find a counterexample. So this is a really good way to try to get a sense of, do you understand what's going on? Let's remove a condition and see if we can find a counterexample. All right, so this is the beginning of being able to determine if a sequence converges or diverges. Why do we care? So here, because of Taylor series. And so again, the nth Taylor series, we'll talk about Taylor series later, is just, f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared, all the way up to the nth derivative at 0 over n factorial x to the n. So the idea is you try to replace a complicated function with a simple polynomial. And instead of using the polynomials 1x, x squared, x cubed, it turns out that for a lot of applications, there are better spaces of functions to use. If you've ever heard of the phrase Fourier series, this uses sines and cosines, expands functions in terms of these periodic functions. And for a lot of people in physics, with amplitudes, this is very useful. Then there's more powerful systems called wavelets, just other sets of functions you can use. So if I want to transmit a function, one possibility is I could just sample the function at a tremendous number of points and transmit the value of the function at all of those points. Well, that's extremely expensive to transmit all of those points. If I transmit 1,000,000 points, that's a lot of information, even today. If I can transmit just a few Taylor coefficients, the idea is if I transmit the Taylor coefficients, you have a smart computer at the other end, and it can take those coefficients and it can reconstruct a really good approximation to your function. So how many of you have ever listened to record? An actual record? Okay. I actually bought a record for my operations research class. I'll try to remember to forget it. From the C millimeter. And you know, this year was a tremendous year of advanced human technology. We had like 12 songs. It was only this big. So now we can transmit tremendous amounts of information. We can store it incredibly efficiently. When you're playing these back, you don't have to play it back perfectly because it's the human ear that's listening to it. If the difference between the actual sound and what you hear is sufficiently small, you will be able to tell the difference. So you only have to play things well enough. Now, some people have a much better ear. Some people have a better sense of taste, which can either be an advantage or if you're a college student in some places it can be a disadvantage. For me, with my dining halls, it was an advantage not to have a good sense of taste. We don't have to transmit the function exactly. I just have to transmit enough to understand what's going on. So what I want to do is I want to talk a little bit about applications. So again, the whole point is to talk to some of you outside about something because you're not going to use most of the material that we're covering in these slides. What you're going to use is the ways to think about problems. And so steganography is the art of hiding images or information in information. I assume everybody can see the tree in this picture. Okay, everyone sees the tree. For $100, can anybody see the cat that is hiding? The cat is at least 1/4 the size of this picture. It is not like a small little cat. You're not trying to just, trick it. Does anybody see the cat? I will teach you how to see the cat. So instead of talking about streaming video, I'm going to talk about sending images. So let's imagine we have an image that's LYW. And so we have a bunch of pixels. There's a couple of different color schemes you can use. I'm going to use the standard red, green, blue. Computers love to work base 2. Why do computers work base 2? It can be stored in bits, on, off, yes, no. Binary. Yep. Binary base 2. So instead of writing things in base 10, we can write things in base 2. So for instance, if I give you 100, this, let's do 314 is 3 times 10 squared plus 1 times 10 to the first plus 4 times 10 to the 0. If I want to write this in binary, what's the highest power of 2 less than 314? It would be 256. So this would be equal to 1 times 256. I'm sorry, 1 times 256. Now the next is 314 minus 256 is 44, 54, 58. So I'm not going to have any 128s. I'm not going to have any 64s. I'm going to have 132. So I've got to get up to 68, right? No, 58. I've got to get up to 58. So I've got to get up to 58. I just did 32. So I need to do another 26. Doing it correctly? Okay, so for 26, what do I need next? I need a 16. I now need 10, so I need the 8. I don't need the 4. I need the 2. I don't need the 1. So it's 1, 0, 0, 1, 1, 1, 0, 1, 0. You put a little 2 there to mean this is base 2. So this is how you would write number 314 in base 2. Okay. So typically, we often use n equals 8 when we're doing the red, green, blue pixels. That gives you 2 to the 8 choices, or 256 choices for each, or on the order of almost 17 million colors. Color the pixel. How many colors do you need to correctly identify? I think you can do a little bit better than 3. I hope. White, black, orange, blue, green, yellow, what is black color? Yes. Yeah, you can at least get the rainbow. Do people think you can at least do 20 colors? If you have a box of Crayola, you can have the 128 box of Crayola. I think you can get something like that. You know, sunset orange. Mac and cheese. So do you think maybe on the order of 1,000 or 10,000 colors? Maybe.
Theoretically,
Yeah, but again, this is similar to what we're talking about with sound. At some point, your eye is not going to be good enough to distinguish between them. And so I think we can agree that on the order of 10,000 colors should be enough for what we can describe, that you're not going to be able to do such a level of refinement. You might be able to do a little bit better than the 128 in the Crayola box. I don't think you're going to be anywhere near the 17 million colors. So what this tells us is that what we're transmitting on the order of 17 million possible colors, we don't really need all of them. This gives us the opportunity to do a few things. So let's just take one of the colors, say red. So it's a number between 0 and 255. So we write it in binary. So each of these R's, because we're writing in binary or base 2, what are the possible values for these R's? What are the possible digits? Base 10, the digits go from 0 to 9. Base 2, they go from 0 to 1. So if I change the last digit, I've moved my color at most one bit, one unit. 1 out of 255, that's less than 0.5%. If I change the last 2 digits, I move at most 4 out of 255, not a big amount. And you might think, well, on average, maybe I'm only moving around 2. So what I can do is if I change just the last or the last 2 digits, it's going to be a very minor change to the color. So imagine we have some text over here that has letters in just black and a white background. Every black pixel I will have as a 1. Every white pixel I'll have a 0. I then take my red tuple and I change the last digit R0 and I make R0 1. If in the hidden message I want to have a black pixel, I have it as 0. If I want to have a white pixel, I can now hide a letter inside an image by just changing the red pixel. If I change just the last 2 pixels, I have 4 possibilities for red. I've got the 0, 0, 0, 1, 1, 0, 1, 1. If I change the last 2 digits of red, the last 2 digits of green, the last 2 digits of blue, how many colors does that give me that I can make now? If I change the last 2 digits of each. So I've got 4 choices for red, 4 choices for green, 4 choices for blue. 64. Hi, it's not the Crayola 128. That's the Crayola 64. That's not bad. So just by changing the last 2 digits, I can hide a lower resolution picture of 64 colors. So here's the cat. Here's the tree. Here is the cat. I was not lying when I said the cat was at least half the size of the image. The cat is everywhere. It is absolutely amazing what you can do. I want to be very careful because this is being recorded. When terrorists are trying to communicate with each other, agencies that are trying to stop them try to look to see is there a lot of chatter between different groups. And so it's always interesting, how do you try to communicate with people? Here is unfortunately a way where you can hide images or messages within messages. So it becomes very important. Can you figure out if an image has been modified? Are there tests you can do? I am not going to describe anything like that where things are being recorded. There are 2 questions I've heard reporters ask in my life that compete with each other as to what is the dumbest question I've ever been asked by a reporter. And one of them was within a day of 9/11, one of the big 3 network reporters asked an airline pilot, so do you have any ways of communicating with people on the ground, ways that the terrorists don't know about to let them know that something's happening on the plane? The pilot was terrific, said, no, there's technical reasons why something like that's not possible. What's your next question? So there's a huge race right now in terms of, how do you transmit things in such a way that you can either slip it by someone or detect that someone is trying to slip it by. When I was a kid, I know there was a small controversy in Boston after the Red Sox game. The next day, some of the stations were just airing highlights. And one of the networks, when they rebroadcasting the sports clip, they edited out the logo of one of the other companies, one of the other news stations that had been broadcasting the game, and they had changed it. Anybody ever watch football on TV and football in real life? What's the best advantage of watching football on TV over real life? The first down line. And now it's amazing when you have people playing, they just go smoothly over that first down line on the TV. I am old enough that I remember when they introduced that and just how bad it was when people walked over it. The image is modified. They do not have first down lines being displayed by laser when you're live at the game. They're adding that essentially in real time in football. So the question is, can you tell when data has been modified? And what are the consequences of data being modified? There's a lot of scientific studies where people have been caught faking data. Some of the reasons that they're caught is, wow, that's exactly the same plot you have in a different paper with different values. You just changed the labels. It's an exact perfect match. So sometimes people are just very lazy cheats. But there's a lot of really good mathematics going on behind stuff like this. And one of the things I want you to get out of this class is, what are the applications of the math you're learning? And already at this level, this is enough to see wonderful applications. We're talking about sequences and series. Rather than transmitting every dot, we can take advantage of the fact that we have powerful computers on the other end that we can send them a small bit of information and then they can try to reformulate the signal. If I have something that's really nice, I can just send a two-dimensional plot of my red function, a two-dimensional plot of my green, a two-dimensional plot of my blue. There will be some issues. I'm wearing a mostly red shirt. There's going to be some discontinuity as I hit where the blackboard is. But there are ways to handle stuff like this. All right, so this is a good place to stop for today.